Okay, thanks for coming, everyone. So my last presentation here in the group in the last week. So yeah, I'm going to present kind of overview of the work that Phil and I did now in the last 2 years in a project together with Huawei. In the last half year, we also did some things that are not shown here yet because, yeah, we kind of have to go with them through it. But I thought like giving a little bit of a kind of a lecture style introduction into the whole topic. So we're going to talk about loudspeakers. We're going to talk about loudspeaker modeling. We're going to talk about fitting them to data, and then and how to linearize the dynamics to reduce distortion in loudspeaker. And the main motivation is that with loudspeakers, size matters. So here some pictures of different drivers. Obviously, we all know these woofers and micro speakers, maybe in smartphones. But I also found this nice earthquake simulator thing, which, yeah. And you can see sometimes we need big drivers if we want to create a lot of low frequency sound, and that's because sound pressure amplitude is proportional to frequency squared and the diaphragm area. So if we go to low frequencies, we have to increase the diaphragm area. And otherwise it's not really possible. Or we have a really large displacement. So one could also have a small woofer like this and just move it far out, in and out, to create a lot of bass. The problem is that with the electrodynamic loudspeaker, moving the coil a lot back and forth, well, normally it's difficult to make a loudspeaker that's linear over this whole displacement range. So we want to have a small loudspeaker that still creates a lot of low frequencies. So it has to move a lot. Moving a lot means it distorts, and we don't want distortion. So what can we do about this? Just to recap for everyone who doesn't exactly know what I'm talking about when I talk about electrodynamic loudspeaker here. I think maybe there are some. So here is just a schematic of a loudspeaker. And the basic principle is that we have a coil here in the field of a static magnet. That's, yeah, and if you apply a voltage at the coil, it creates a current. The current and the magnetic field creates a force and pushes this diaphragm outwards. And then there is the surround and the spider. There's a suspension system that holds it in place. And then we have like a mass spring system, but that's forced by current. It's forced by the Lorentz force acting on the coil. Yeah, in practice, it looks like this. So if we want to model a loudspeaker like this, then we have to find what are the dynamical equations that model it, and the kind of two basic ones I just shown here don't look so much at equations, but it's kind of a multi-domain system. So there's some electromagnetic forces and mechanical forces as well. And this here are then the one equation for all the voltages in the system. This is Kirchhoff's voltage law. And then we have down here just Newton's law for the force, right? And the quantities that describe then the motion of this whole system, the so-called states, this current here, the position, and the velocity. And for this simple loudspeaker, it's 3 different states and describes totally the state of the loudspeaker. And then we use the differential equations to describe the dynamics, right? We solve a system of coupled differential equations to then find out, given a certain input, how does the loudspeaker move? So now this is the simplest linear loudspeaker model. And in practice, we don't have an idealized loudspeaker, but we have some complex physical system, and there are many nonlinear effects that happen. So, for example, the force on the loudspeaker it comes through this coil here, moving in this air gap, and you can see the coil has a finite length. So if we push the coil out very far, it will not be so much anymore in, or it can get out of this this so-called air gap where the magnetic force is, or the magnetic field strength, and then the force on the coil will be lower, right? Or for example, this spring here, or the surround, which is modeled as a spring, if you push it out at some point, it will stiffen a lot. It's not an ideal spring. It's a nonlinear spring at large displacements. So in my project, we looked at many of these different effects here and looked how to model them. I will not go into the details of the models, but yeah, this is kind of what you have to work with. So in practice, this creates distortion, and just a quick reminder of what it does. What does it mean if the loudspeaker distorts? So a very simple way to illustrate it is that if we have a two-tone input, so we have two frequencies, maybe a low frequency, maybe below the resonant frequency, and a high frequency. Then in a nonlinear system, this will add extra frequencies at the output. So in the pressure or in the acceleration signal of the loudspeaker, there will be additional frequencies which were not in the input. And this is what we call when we say it's distorting nonlinearly, right? It creates additional frequencies, and they are not pleasant to the ear, or can make it even impossible to understand what's said. I mean, we all know, like being in the airplane and someone talks into the microphone and you don't really understand what they say. Okay. So the goal now of modeling is to reduce the harmonic distortion here, but also intermodulation distortion. So harmonic distortion would just be additional frequency components at multiples of the fundamental, and then intermodulation distortion is if you have then multiple frequencies, then they interact in a nonlinear system, they interact and they create more distortion components. So in practice, then you come up with some complex system of differential equations, and you maybe have seen this slide before, but this is just to illustrate what kind of systems we deal with. So it's always a system of coupled differential equations where we have, for example, an equation that models the evolvement of current over time. So here, current, of the displacement, of the velocity. And then if you make the models more complex, you can also have some additional internal states which you cannot measure. For example, here, so this is a model that uses something, it's called an L2R2 model. So you have some additional modeling states, but they're not directly measurable. And then you have some nonlinearities, for example, the force factor. So the way the proportionality factor between current and the force. And then you model this as a polynomial in the displacement. So maybe it's really high at the center position, but if you push out the force, the proportionality factor gets lower and you have less force. And this creates, this represents then these nonlinearities. But I mean, for this talk now, specifically, we just condense all this and we just look at these kind of systems. So you have some differential equation of some multivariate state. So here, for example, I, X, V, and I2. And this is independent on some vector field F, which is parameterized by some parameters theta. And these thetas are all these polynomial coefficients, for example, or the mass of the system. Then we have some input U with the state Z. And in practice, we cannot observe all of these states. We can only observe a certain output here Y. For example, a certain output could be that we only measure what is the current and what is the velocity. Yes, and so then the goal will be from this Y here, from a measurement of this Y, to estimate all these other parameters. So the measurement looks like this. We have a system of drivers. We have some driver here, and we have a laser that measures at a certain point the velocity of the driver. And then we play a signal through it, and we have some shunt resistor over which we can model, over which we can measure the current that goes to the loudspeaker. So in a measurement, you would actually measure what is the exact voltage that you put in the loudspeaker, what is the current, and what's the velocity. And from these three quantities, we can derive all these parameters. And how does this then work? So what's the, we cannot see the title here.
Actually move. So you can probably go on the more, then it says, no, not really.
On my computer, it doesn't say, but I'll just move it. Maybe the lower right will be a good spot, or lower left, like this. All right. Okay. Now we made a measurement, and we want to know how can we estimate the parameters of the system. And yeah, here I want to quickly explain how do you do this in practice. Yeah. So we gather a data set. This will be what is the initial state of my system at time equals 0, and what is the input, and then what are my outputs. And normally we gather them at discrete times, so there's some discrete time signal. And then we do some pre-processing. So normally we downsample the signal, and then we interpolate the input signal. And if we interpolate the input, so we have some sampled u, and then we interpolate it to get the function, continuous function of t, then we can reformulate our vector field f as being a function of the current state and of the time t. And then we can actually apply ODE solvers to solve it. And then we solve a non-linear least squares problem where the forward model that we want to fit is solving the ODE. So so we get some discrete time states z, and then we use the output equation to get our output y. And so yeah, this is a weighted nonlinear least square problem, and because we have a physical system and many of these parameters, there are physical parameters, like the mass should not be negative. We have some box constraints on all the parameters to be positive. Yes, and so in principle, it's just a nonlinear square problem, and you have this ODE solver at each step, and there are some technicalities. So, for example, what is the gradient, or what is the Jacobian then of your problem when you have an ODE solver in there? And I will later quickly introduce some software package that computes all this automatically, but you can also compute, for example, a Jacobian of an ODE automatically with respect to some parameters. Sorry, not automatically, analytically, by solving another ODE problem. So this is one of the ways to then compute like this sensitivity equation, so to say. So this is all good, but there are many kind of issues actually when you then do the solving in practice. So now the last 5 months I've been battling a lot with the practicalities of solving a nonlinear least square problem with such an ODE solver in it. So very often, so optimizer can get stuck in a local minimum. It's a non-convex, nonlinear problem. It can happen that your system is actually not identifiable. So, for example, you can imagine if you have somewhere in your equations 2 parameters as a ratio, then you cannot find out what is each of these parameters. You can only find out what is the ratio. So you have to re-parameterize your problem to be what is said identifiable. And there's a term structural identifiable, which means if a system is structural identifiable, it means you can find all of the parameters uniquely, maybe globally uniquely or locally uniquely. And it's not always so easy to do this, to find out about this. Then, because you're solving an ODE, the ODE can diverge, the solution of the ODE can diverge. And this can be also So this is then related to also the optimization procedure, right? So maybe it steps into a region where the OD diverges. Yeah, very, very annoying. Then if you have an adaptive ODE solver, it can also step into a region where the adaptive ODE solver is very slow. It kind of never really converges. So this is also something. And then the ODE solver has lots of hyperparameters. So it's a tricky problem. But you can do some things. So for example, when your ODE turns into like a very stiff ODE, so it means it needs very, very small time steps, you can just say after some time, I reject this parameter set, and then the optimizer just tries another parameter estimate. Structural identifiability, you can check. There's some toolboxes, like for example, the Julia package structural identifiability, just strike code in MATLAB. And they are actually kind of okay. If the systems get too big, they're not very useful though. So if you have a system with, for example, 80 parameters in 11 states, I cannot solve it on my computer. So then I'm solving some kind of similar system, and I just hope for the best, that they're still the same. Then one important step is this reparameterization to make it both structural identifiable, but also scaling parameters to be of the order of 1, or states to be of the order of 1, such that the problem numerically is easier to solve. And that also means, for example, avoiding divisions. So if you have a parameter that only comes as a division, replace it by a parameter that's not a division, and then it's always okay if this parameter is small. Yes, and then finding good initial parameters for the nonlinear solve by solving a related approximate problem. And this is what I will talk to in the next slide. And then, yeah, you can also make it faster by compiling it and stuff. Now, I'll just quickly talk about it later. So, so we want to find a good initial minimum, initial parameter estimate. And so one way is you can, of course, say, okay, loudspeaker, I know the mass is maybe 10 grams and BL is around the order of 4. And that is already a good guess for this first problem to solve. And here is the idea that we have a nonlinear system. And then we linearize it. So we find what is the approximate dynamical system at for example, the state x equals 0. So we can linearize this and find like a linear ODE system like this here by computing all these Jacobians for these different matrices. And then we know that the transfer function, the linear transfer function of this linear system, which is dependent on the parameters. And then we can, in this first step, just fit the transfer function. And here, what I'm doing is I weight my transfer function always with the power of the input signal. Because, so for example, this here is the cross-spectral density divided by the outer spectral density. That would be the transfer function, right? But at energies where you have 0 energy, it's not a well-posed problem, right? And if you just then weigh times the input energy, you always have a well-posed problem, and you don't have to think about regularization. Of course, you could also add some regularization. So here it says, you can see that a little bit still. So this is a convex. This is a non-convex problem still, but it's much easier to solve than the non-linear non-convex problem. So this is also a non-linear problem now, because we have a linear system, but we're solving for these parameters. So this problem is non-convex in that, but it's much easier to solve. We still need some good guess, but we can get a better guess with this. And then below this here, I'm saying, the great thing is this can't diverge. So this problem is always kind of easy to do. Okay. Just skip over this. All right. So now we have a model and we have parameters, and now we want to linearize our loudspeaker. So basic principle of it's called input-output linearization in the control literature. So the basic question is, we have some physical system, like here, this real loudspeaker, and we have a really good model of this loudspeaker that we just identified. The question is now, what input can we put into this loudspeaker, this input U, such that the output Y of our physical speaker is the same as the output of a linear, like ideal speaker, a speaker that doesn't have any distortion, that's you know, it's played with some music signal, for example, R. So we want to find some function U here that's dependent on our desired input signal, but it's also then turns out it's dependent on the states of our two systems here. So we want to find out what is this function U that kind of pre-distorts the input to the loudspeaker, such that the output of our loudspeaker is the same as the output of a linear reference system. Kind of makes sense, right? So how do you find this U? So that's the question. Which U makes Y take YR? So it's kind of super easy to derive, so I thought we'd just do quickly here. So we have our differential equation that models our system. And now the question is, how do we get some equation that makes a relationship between the output of the loudspeaker and the input? And if we have such an algebraic relationship, then we can just solve for the input such that we can compute the input for a certain output. And we can do this just by taking derivative of this Y here. Do some chain rule. See that here, this X dot, we can put in our differential equation, and we get an equation like this here. And there's a certain formulation. So these kind of dot products between Jacobian and another vector field, you use these Lie derivatives here, but it doesn't really matter. It's just dot products between functions. So now we have actually already an equation between Y dot, between some derivative of the output and the input U. So if this term here in front of you is non-zero, we can divide by it, and there we have it. We have an equation that gives us the input for a certain desired derivative of the output. It's not the output, but it's a derivative of the output. And if this term now is non-zero, we say the system has relative degree 1. We have to take one derivative of the output to get a relationship to the input. Let's say, okay, you know, it is 0, which often happens, okay. Then we get an equation like this. There's no U here, but we can again take a derivative of Y. And maybe now this term in front of you will be non-zero. And then we get an equation like this. And I mean, you see this schematic here. So in general, we say that a system has relative degree, some relative degree gamma, if actually all of these up to gamma are 0, all of these terms in front of U. And then at that point, we can reformulate for U or solve for U and get this little equation, and that's where all the magic happens. So let's look at this just a little bit in detail. What does this actually mean? So this term here on the right, that's the derivative of the output Y of our real system if we don't have any input. Yeah, so if at this point in time we don't have input, and then this term here on the left, it was here this gamma derivative of the reference system. Here I just put the equation for a linear system in. So if the gamma derivative of our real system is equal to the gamma derivative of our reference system, then we don't need any input, right? This here is 0. So, and then also this error in the derivative here is 0. That means at this point, we don't need to do anything. We already have the right derivative to drive our system. But if they're not the same, then we have this U, which kind of tries to make it the same. And this is scaled by, you could say this is degree of controllability. And you can remember that this is always the term that's in front of the U. So if this term gets really, really, really small, it means that there's no way I can drive my derivative of the output right now because it's so small. I need a huge input to make any little change in this derivative. So you don't want this to be 0 or near 0, so you want to be bound away from 0. And this is kind of how you interpret this. And for a linear system, you can easily compute what is the derivative, the gamma derivative of your output, and then you get an equation like this. And you can see this now depends on the state of our real system, of the nonlinear system, the state of our reference system, and this reference input. Okay. So now we found out how to compute U given X and given Z and given R. But how do we compute a whole signal? We want a whole signal. So, and for that, we can just solve a system of coupled differential equations. So we have here our nonlinear system, we have our reference system, and they're coupled then by our precompensating input here. This U, our equation that we just talked about. So what I do, I solve this coupled system of equations, and then I get X, Z, and R, and then I apply this equation again. I mean, one could probably also get U out by first solving it, but yeah, I solve it and then I compute U. Right. So now let's look at some results. Let's look at how this looks done in practice. So this is these little loudspeakers that we have so many of, and here on the right we see an input signal, a two-tone input signal into this driver, and in blue we see just the two tones. So it's a low frequency and a high frequency at 20 Hertz plus 1 kilohertz, and we can see that then the compensated input, you know, is at some point it's much higher, and you can already kind of imagine why it has to be really high here, because here the low frequency excursion will be really high, and probably there's something that hinders the loudspeaker to move as far. For example, the stiffness gets stiffer, or the spring gets stiffer the further you move out, or the force on the spring gets less because at the because the coil moves out of the air gap. So if you look here at displacement, so now this is the displacement of the voice coil from the resting position, then you can see that in the nonlinear system has this distorted waveform, and then it's exactly here. If I just go back, it's exactly here where we need now more. We need to put in more energy to move the speaker even further, right? And this is what the compensating loudspeaker does. Like or the compensator does. It moves and forces the loudspeaker to behave in the way we want. So this is now just velocity. So here we can see, yeah, also in blue the nonlinear model, and then because this is a simulation, in orange and green the linearized model, and they just overlap here because it's a simulation. So now when you do this experimentally, here I'm showing the output signal, that the desired output signal, and then the output signal that you actually measure, and those are not always exactly the same. So in what I'm doing right now is that I model the amplifier or the whole kind of output chain, like audio interface and amplifier, as something that has just a gain and the delay. But it seems like this is not sufficient. I mean, to have to compute a perfect match between the output that you actually want and yeah, and the output signal, the output voltage that you then measure. So right now I'm getting like a 0.5%, 1% error sometimes on these. And then here we can see an experimental result on the displacement. So the real loudspeaker distorts. And then these other curves here are all simulated, measured, and simulated from the measured output compensated signals. And I mean, they at least look much better than the uncompensated. They look quite good actually. Okay, let's jump over this. So here, what we then like to look at to quantify how much do we reduce distortion, we look at the harmonic spectrum and the intermodulation spectrum. So here on the left is harmonic spectrum. So we have an input signal of 35 Hertz. So we have here fundamental, and then we have the higher order harmonics. And in red, you see the uncompensated loudspeaker, and then in green is the compensated one. And you can see that we reduce the harmonics here considerably. So this is a favorable case. So I showcase it here where the results were really nice. So this is going from 45% distortion to 9%. And in the intermodulation spectrum, we can also see that the intermodulation distortion components here, they're reduced quite a lot. And here the TIMD, the total intermodulation distortion, goes down from 2.3 to 0.4%. Okay, we can do another investigation on reduction of the nonlinearity. So for example, instead of having two pure tones that are constant, we can sweep with one tone, and then we can look at the harmonic distortion over frequency, and then compute the total harmonic distortion over frequency. And this is what we see in this graph here on the left. So this is total harmonic distortion, and this is the frequency here of the tone. And in this example, there's actually also quite a nice reduction. And so I guess we're here somewhere around 27 maybe, and here 12. So yeah, this is a nice result. And then on the right here, we see the corresponding magnitudes of the fundamental and the harmonics over frequency. And the way to read it is that, for example, you look at, okay, this is the level of the fundamental. And then at that level, the second order harmonic is at this level, and then with compensation, it's reduced like this. So the frequencies, of course, here are the frequencies of the fundamental, not of the higher order harmonics. So they are aligned in that way. All right. Okay, and then kind of the last way you can also look at this problem is now we want to have not only sweeps or two tones, but some kind of random signal. So for example, pink noise could also be music. Here you use pink noise, and then you look at a non-coherent distortion. So non-coherent distortion is computed from the coherence. So you remember coherence gives you some idea of how much of the output energy is linearly dependent on the input. Yeah, the ratio of the output energy, which is correlated with the input at a certain frequency. I hope I said that right. And the non-coherent distortion is kind of just the opposite, right? And also you can see here, so uncompensated, we have quite a lot of non-coherent distortion, but with the compensation that goes down. And then here these lambdas, this is similar to a total harmonic distortion, but wideband, and that's also reduced. And the interesting thing here is that even though in this plot here, it looks like we only reduce distortion below the resonance frequency, actually all these harmonic components there can be also above the resonance frequency. So we don't only reduce distortion at this kind of not so useful frequency range, but there's actually distortion reduced at higher frequencies, a frequency above resonance, as you see here. Okay, so then now at the last, so I mean, you guys all know about this, but now it's also public. So there's a package in Python on my GitHub called Dynax. And here the idea was that all these things that we're doing, or that I've been doing, you know, how do you do this easy, automatic, and all these things. So now there's this Python package out. It's based on on JAX, which is this Python library to do automatic differentiation, but also compilation. And then Diffrax here is a library for the ODE solvers. And then we can do all kinds of things. So for example, we can estimate ODE parameters, both like do this linear estimation of the parameters and the nonlinear estimation, compute some covariances of our parameter estimates. We can also fit to multiple experiments at the same time. So not only one sequence, maybe you have multiple levels of an input signal and you want your model to be good over most of them. But it also makes this input-output linearization very easy. You kind of, actually I will come to this in the next slide. Exactly. So have a look at this if you're interested. And I'm not going to go into detail at all, but the main idea is that in Dynax, you just define like a class, and the class defines, for example, these functions f, g, and h. So this is just a nonlinear mass spring damper. We all know how that looks like. And from this, it can automatically compute the linearization law, for example. So it's totally a work in progress, and the documentation is not there yet, but if it's interesting for anyone, then just reach out and I'm happy to look at your problem together. All right. Super over time. So takeaways. We learned about the distortion problem. We learned how to how that loudspeakers, they have to move a lot of air, then they distort, we don't want distortion. So we can do this input-output linearization, and now there's a package and you can do it kind of easier. I mean, for me, the biggest kind of unsolved problem is like this robust estimation of the models. It's kind of easy for all the models I looked at until like 5 months ago, and 5 months ago I looked at bigger models, and it's just a hassle with these parameters, and I'm sure one can do it better, but I have to learn still how to do this in a robust way. And then a kind of takeaway also is that the how good the linearization is bound on how good the model is. So if the model is perfect, the theory of the linearization is exact. So good models will mean good linearization components. So there's not so much work that needs to be done there. And when I talk about model errors, I mean, these are lumped element models, so they're totally approximations, right? And then with time variant systems also, the voice coil can heat up, and the rubber material gets old, and I mean, all the things that happen, I guess, in a loudspeaker over time. All right. So this was my last slide. This was also my last presentation. Thank you all for coming. And yeah, it's not the final goodbye today, so there's the whole week. But yeah, thanks for your attention. So we totally have time for questions also. If you guys online have questions, the easiest would be to unmute, maybe quickly say who you are and ask something. And otherwise, are there questions here in the audience? Okay, Antonio.
Hello again. Very nice presentation. I had a question with the compensated system. If you have a very transient signal, how well does the system kind of like react? Whether you will have some kind of, delay in between capturing this transient and then actually compensating for that.
Yeah. So in principle, there's no inherent delay, but of course, if you compute a compensation signal, you need to know. So you need to solve your ODE somewhat in advance before you send it to the loudspeaker. But there's no like FRR delay or something like that. So there's only the processing of the compensation signal. And let's say you run this in real time together with your system. I don't think that would be a problem. All right. Oh, this is a far one.
Thanks, Franz, for the presentation. I was like actually wondering, like in slide 21, when maybe you can show it. You show there like the non-linear model and then some linearized, and then you talked about the differences in amplitude, but also it seems there is a bit of like a difference in phase. Can you comment on that?
Yeah. So, so the question here is, what reference model do you use? So, what is the reference model your loudspeaker should strive to act like, right? And this could be any model. Here, the reference model is doing this linearization, approximate linearization, and that system just apparently has like, you know, more of a phase change, but you could design that in a way that they more align maybe. But yeah, that's there is the freedom to choose.
Like your ideal system, like
yeah. So someone was just saying that if you want your system to be have more of a phase delay, let's say, but it's continuous time system, so you can't have a pure delay in it, right? You can only have some kind of stronger phase shift in some way. Yeah. Interesting also is that your reference system doesn't have to be linear. Your reference system could also just have a non-linearity that you like more. So it's not required that it's linear. For example, and it's people in auditory maybe might like that. So at large excursions, you want your loudspeaker to be somewhat protected and to not require too much power maybe. So this is now a design in the design freedom. Yeah. Yep. Any questions online? No questions online. But we got Jonas here.
Yes. So now this is for ordinary dynamic loudspeakers. Would it work also for the balance armature, for example, some other kinds of loudspeakers?
So the technical requirement is that your system has this well-defined relative degree. So if we go back, yeah, right. So the dynamics have to be such a way that this relative degree is well defined. So all these terms are zero until at one point where they're not zero. And so in this way that it's done here right now, it's not feedback control. So so even though there's where do we have that slide? So even here it looks like there's feedback. We don't actually measure the real state. We estimate it when we solve the ODE and think our solution is perfect. So it could be that I think I remember someone here saying that for the balanced armature that it can get unstable also if the armature moves too far, it can kind of get in contact. Is that right? And maybe this is then a problem. So if the system is unstable and you don't have a good estimate of the states, then many things can happen, I think. Yeah. But otherwise, I think totally. So you just need your system as a system of differential equations and not as a lumped element kind of structure, right? Like, because then it's, well, you have to derive the differential equations and then you can apply it. Yeah. And Finn is asking a question.
Thanks, Franz, for basically summarizing control theory 2 in 45 minutes. Maybe you could show the slide again with the compensation signal. because it seems like very quickly you need a lot of power into the speaker, right? So I think you already mentioned a bit about that maybe you need to then actually not linearize the system, but make it behave in a reasonable way, right? Because I think manufacturers don't want a compensated speaker to destroy itself at the first party, right? So
Yeah.
Any thoughts on what's a good strategy for that, or what should be considered?
Yeah, good question. So, I mean, so practically, I don't have much experience on loudspeaker design and all these kind of things. So and I'm not the first one to say also that now, like, if you now can design your speaker to, I mean, if you know that you have a compensator like this, you can maybe think about it in the design of the speaker and then co-design them in some way, and maybe then have a good estimate on what are the limits that I don't want to get to. I don't know how to well estimate what will the power output be. I mean, you can always solve the ODE problem and then see what will the power output be. What you could also do maybe is, so I mean here, this screams here like you could also add some kind of optimization where you have some, so you could say that it's, yeah, I mean, I'm sure you could reformulate this problem not as having this explicit equation for u, but have like an optimization problem which weights both having this error here small and having the magnitude of u small. So and then then you have to fix some hyperparameter, but that's maybe also a way to regularize with the input signal. Yeah. We'll show.
The last question or some more? Thank you, Franz. Thank you for being with us for many years. My question is, I mean, maybe slide 21 is a good slide to talk about. So there's a huge difference, or I mean, at least in this plot, I can see the differences. How much human kind of perceive this kind of, yeah, not beautiful shape of sine wave. How much can you gain by this?
I was thinking yesterday about this question. I was like, damn, I really don't know what the J and D is kind of with distortion. I guess maybe Finn, you have a little bit of an idea. Okay, he's shaking his head. So it's a really good question. I have totally not even looked at the literature about it. So also, what does this here mean? This going from 45 to 9%. Okay, the numbers look good, but yeah, that's a great question for sure. I wasn't thinking about it until yet, more or less at all. But it's definitely a valid question also to think, is this useful? Is it not useful? Right. So yeah, 100%. And Finn has
Comment to that, it's definitely more important to get rid of the intermodulation. Harmonic distortion on its own is quite difficult to detect, but as soon as you get those, because most signal materials, most music will have harmonics already there, right? So you don't really notice that so easily. But the intermodulation is what's important to get rid of. But is it important? Is it enough to get down to 1% or 0.5%? I mean, I don't think there's a clear answer for that. Still, yeah.
all right. There are no questions here. If anyone has a question online, then now is your last chance before we'll end the session. And otherwise, just reach out if you have questions. And thank you everyone for being here today.
Sounds so great.
Yeah.
Yeah.
Yes. Ah, and I wanted to record it. Of course, I forgot. Damn it. Anyone wants to chat here? I'll leave it open for a while.
Maybe you just close the session.
Yeah. Okay.
I gave you